Hi guys, in this section I'd like to talk to you about friction. Now I've lined up a couple of objects on here and I'd like you to think about how easy it is for me to move them. So if I go on this tin here, I push that along and it's really quite easy, just a gentle push. But when I go on here, I have to start to push quite hard before it will move. And you might say, well, okay, that's clearly a lot heavier. And it is a lot heavier, and that does definitely make a difference. But also, there is this idea of what it's made of. This is a real shiny tin. And this is like a roughened plastic. So that rough area there is making a difference. So this is really smooth and this is rough. And when I actually go onto the smoother bit of board, it does move easier. So friction hinders motion. And things that will affect it affected by the mass of an object and also the material the object to. So in thinking about the mass, there's something else I need to think about too. So for example, if this is on here, that's not moving. If I start to tip it up, it eventually does move, and the more I tip it up, the more of a difference it makes. So more of a slope affects that, and we need to consider that as well. So what's happening? So let's say I want to push with a force there, and I'm going to hold back with a force there. Now, actually, another thing that made the whole much different was the fact that it had a bigger surface area. But we're not going to do that. We're going to model as a particle, because surface area would really take the issue much harder. So if I've got that, what I had in the beginning, just got a little bit smaller. If F equals P, it doesn't move. You would say that's in equilibrium. And if P is greater than F, it moves to the right, or it accelerates to the right. Okay, but F can never be bigger than P. And actually it is always just big enough to counteract P. Until it reaches a limit. And so you'll notice here, as I'm pressing, the friction is the same as what I'm pressing with, until a point when I press past that maximum friction. So F max is what we call the limiting friction. And that is equal to mu R. Now mu is the coefficient of friction, and that relates to the material, and R is the reaction force. And of course that is directly related to the mass. So friction, the maximum friction, is always going to be mu, the coefficient of friction, times R, the reaction force. And you could see that when you tip the plane up, you've got R coming through there, then mg here. We learnt last time that that is theta and that is theta, and that is a right angle. R that's mg cos theta. So the block is not going through the plane, so we must have an equilibrium parallel, perpendicular to the plane. So R equals mg cos theta. And if you think about the graph of cos theta, as theta gets bigger, cos theta gets smaller, so R gets smaller, and F gets smaller. So the reason why things slide more easily, when you lift it up like that, the reaction force is getting smaller. So because we're looking at F equals mu R, to keep the friction holding it, what is opposing it, which is this here. So we've got obviously got mg sine theta, and we would say when F is smaller than mg sine theta, the object slides down the plane. Obviously as this is being lifted up, the sine graph gets bigger and bigger and bigger, doesn't it? So as this is lifted, the impact of this mass, of this weight, makes more of a difference, and the reaction is reduced. So you've got more force pulling down and less friction together. So that means it slides much more easily once it's tipped up. So we've got this idea of it being on a plane, and then the idea of F max equals mu r. Remember that friction only is as big as it needs to be until it reaches a limit when it can't hold out any longer. One final example is if I'm just saying, okay, I'm pressing on there, friction can't push me back, and I press a bit harder and friction is getting towards the limit. Remember I spoke about the limiting friction, and we might talk about limiting equilibrium, and it's just about to move. So in general, friction most friction is less than mu r. When it reaches the maximum, it goes to F max equals mu r, and what was I going to say there? And this happens when accelerating. In limiting equilibrium, or about to slide. They're the key words that we're looking for there. So generally we work with questions where we're looking at the maximum amount of friction available. Obviously here, when it's dead flat, and if there was no force acting on it, we would not, the friction would be zero. Friction's zero on this at the moment because there's nothing acting on it. When I lift that up, now there's some friction holding it back, stopping it from sliding down, which is what the component of the weight wants it to do. And as that goes up, the friction is getting less and less because the reaction's getting smaller, and the component of the weight is wanting to pull it further down. So the higher up that goes, the friction gets less and the force pulling it down gets bigger at the same time. So quite a tricky topic, but we've spoken about this type of thing, and taking that on board is really important. We know about equilibrium of forces, we know about things balancing up, and when you've got a resultant force that causes an acceleration. So F equals ma runs throughout these questions, and I hope that gives you enough to make a start in a nutshell. Okay.